And hello, welcome to this video of we're gonna kind of just continue where we left off for this Blazes boundary layer. So yes, we needed some boundary conditions, and what are some of the boundary conditions we can take? We already said that the no-slip condition gives u equals 0 and v equals 0 whenever y equals to 0, i.e. at the boundary layer. Of course, the other thing is that when y goes to infinity, right? Y goes to infinity. What will you expect? Okay, you will expect what do you call that? U to go to u infinity, right? So that means that it will approach the free stream velocity as y goes towards infinity. Okay, what else? For the boundary condition in the x direction, one thing you could put, I'm not sure if it's redundant or what, but when x equals to 0, okay, x equals to 0, alright, and y not equals to 0, okay, you will have u equals to u infinity, which is the free stream velocity, and that's pretty much all you need. Okay, so now that we have our boundary conditions, we are able to start what do you call that? Start looking at our solution, similarity solution. How do you start doing this similarity solution? Okay, we already made life slightly easier for ourselves by introducing the stream function. The stream function actually combines the u velocity, the x velocity, and the y velocity, which is v, into one parameter. Okay, that combines two. So the remaining thing is for us to combine x and y, and it's not exactly obvious to know how to do how. I mean, the stream function itself was someone else invented it, figured out it could work, and just put it here, and that's Blasius who did it. So Blasius, I think it's Blasius. It's a German name. Yeah, German, Deutsche. Yeah, so German physicist or engineer, I don't know. Yeah. So Blasius, von Blasius. Okay, so he decided to come up with the stream function, and it worked. Okay, so of course the stream function is based on the continuity equation, so there is some physical basis for it. It's not completely a random assortment of variables, so at least there's some physics behind it, some intuition you can get. It satisfies the continuity equation, and at the same time it combines u and v. Now how do we combine x and y? Okay, there's a systematic way to follow it, to do it. Let's see. Okay, so okay, let's call this a similarity transform. Okay, yeah, we use the stream function to help us deal with the x and y coordinates. Okay, let me start my stopwatch. I don't want to go too long. Yeah, so we had the stream function to do the x and y velocities. So we need another function, something like to help us figure out what eta should look like. Now, how do we start to get these combo parameters? All right, combo parameters. There's of course a proper name. Okay, these are actually called similarity variables. Okay, this eta here we call it a similarity variable. How do we get it? Okay, so I want to refer you to the von Blasius's original paper. Well, it's not exactly the original paper. If you search for Blasius's original paper, it's called you can just search Naka Blasius online. You will get that. You will see that it's available on NASA, and the National Advisory Committee for Aeronautics. Okay, and then the title of this document is The Boundary Layers in Fluids with Little Friction by H. Blasius. Translation of Kretschingen in Flüssigkeiten mit kleiner Reinbuch. I'm not sure if I'm doing it right, but kleiner means small. I think Reinberg means friction. Okay. Never mind. This word should be, I think, fluids. Okay. So the original paper is written in German. So unless you know German, you're not going to be able to read it very well. But thankfully, NACA, the National Advisory Committee for Aeronautics, they've kindly translated it for us in February 1950. Okay, so it's all nicely typewritten out for you. You can search it online. Just put NACA Blasius in Google, and you can go to NASA. Okay, NASA actually has some of these papers online. See, it's a NASA paper, and then you just click on the PDF. Everything is available for you for free. Yeah, this is a NASA's repository. Okay, so you can see they did the non-dimensionalization here to get the fluid equations. Then he goes on a little bit more, and so how he actually obtained this similarity variable. He actually again non-dimensionalize it. So it seems that non-dimensionalization is a good way of helping us determine not just important non-dimensional groups for scaling analysis, but also to help us determine what similarity variables are. And if you keep looking, you will see that the similarity variables will be something like so. See, u equals to some sort of these are the similarity variables here. Okay, these are the similarity variables. You have k u bar over rho. Now u bar here is actually just the free stream velocity. I think last time the typewriters they used this what do you call that? This convention. K is actually the dynamic viscosity, and rho is the density of the fluid. So then x is of course your x coordinate, y is your y coordinate. Then you have a factor of half in front for some of them. So yeah, it's really let's just first go through how some of these things are determined for us. Okay, how some of these things are actually determined for us. Okay, so this is Blasius's paper. He didn't show all the steps, but I'll show you some steps. Okay, some steps. All right, so okay, based on Blasius's paper, translated by NACA, NACA, National Aeronautics, whatever. I'm sorry, no disrespect intended. It's good to non-dimensionalize to find these similarity variables. Okay, so that's what we need to do. So let's do some non-dimensionalization. All right, so we introduced a stream function, but now let's start by introducing a non-dimensional stream function, similar to how we actually deal with how we actually deal with what do you call that? How we actually dealt with the velocities. Remember we were scaling everything before? Back a few videos ago. Where was my scaling analysis? How to drop terms? Yes. Okay, I didn't have them all together in one place, but right. Yeah, I did not have them all together in one place. But yeah, see, I did some scaling before. How to scale the x, how to scale the y, how to scale everything else. Okay, so I hope you remember some of that, because you're gonna do more of that again. So we introduce the non-dimensional forms of the stream function to help us find what the so-called how do you say, what the similarity variables should be. So the non-dimensional stream function will sort of be the dependent variable, because the velocities are captured in this stream function, and they represent the y, the x, y and x velocities, and the other what do you call that? The other variable we are not so sure yet. But let's deal with what we know. Let's non-dimensionalize this stream function first. Okay, so let's see. Let's copy this down. All right. So let's non-dimensionalize the momentum equations and see what we come out with. Okay. So so I'm going to paste this twice, because the second one I'm going to non-dimensionalize it out. So let's non-dimensionalize this first term on the left. So psi becomes psi star. Okay, psi equals to psi star times psi naught. Okay, so psi star and psi naught. So that's the first term. Okay, so on top we will have psi naught, and of course at the bottom we will have y equals to y star times the characteristic y length, or y velocity, y length scale. What's the y length scale? That's actually the our boundary layer length scale, which is of course the boundary layer thickness. Then let's look at this term. This term here is actually del by del x of del psi del y. Okay, del psi del y, again we can actually non-dimensionalize it in the same way. Psi becomes psi star, y becomes y star, and then you multiply the psi and the delta p outside. So I'm just going to put a square, and let's think about this term. Del by del x becomes x star into L. So x star into L, so L will be at the bottom. Okay, and let's look at this one as well. We have a del psi del x. Del psi del x, okay, del psi del x, we will change it into del psi star del x star, and we'll have a fraction on the outside. Okay, what's the fraction? Okay, you should have psi naught on the outside, and of course L. I hope you can see where I'm going with this. Okay, so del psi del y squared, del 2 psi del y squared. So let's do del 2 psi del y squared. So psi will become psi star, y will become y star, y squared will become y star squared. So there'll be another psi on the outside, another psi naught on the outside, and then you have delta p squared. Okay, so you can see these two are actually going to become quite the same. Now the last one, pretty straightforward as well. We'll change our psi into psi star, y cube into y star cube. Okay, and then we will group all the terms together with nu, which is the kinematic viscosity, otherwise dynamic viscosity over rho. Okay, psi naught will be on top, and delta p cube will be at the bottom. Okay. Of course, as a whole, each term here is not, it still contains a dimension. Okay, this term here is non-dimensional, of course, but these terms here actually contain, these coefficients here actually contain dimensions. So how do you do with it? We just divide throughout by this term on the left hand side. We divide throughout by this psi squared, psi naught squared over delta p squared, and then L. So we multiply L and delta p on top, Alright, we multiply L and delta P squared on top and divide by psi P squared, or psi naught squared, sorry. So divide by psi naught squared, okay, psi 0 squared, and delta P and L, delta P squared and L will remain on top. Okay, so this is how we do it. Now, of course, after some terms cancel out, let's see. So delta P squared should cancel out with delta P cubed at the bottom. Okay, and psi should cancel with the psi naught squared. Okay, so pardon, there's still a little bit more to go. Okay, so we have sort of this dimensionless group here. Okay, dimensionless group. Okay, what's this dimensionless group? Okay, we have a nu, we have the L, and we have delta P at the bottom, and of course psi naught. So this is the dimensionless group that so-called comes out. It's sort of analogous to Reynolds number, but it's not really a Reynolds number anymore. Okay, but this is good. Okay, this is good. What should this be? This should be on the order of magnitude of 1. But now we are not really dealing with order of magnitude anymore, right? Okay. Yeah, we're not dealing with order of magnitude anymore. We are not dropping terms, but we want to convert. Let's say this sort of dimensional equation, this stream function equation, into a dimensionless form. Okay, we want the terms, want the dimensionless form. We want the equations to be non-dimensionalized exactly. Okay, we want the terms to be non-dimensionalized exactly. So we want this whole thing over here to sort of disappear. So if the equations look like, okay, they look like this. I mean, that's the idea of this whole non-dimensionalization process, so that you can find the groups. Okay, you can find the groups that you want. So if you want the equations to look like this, where everything is nicely non-dimensionalized for you, very neat, okay, so then this parameter cannot just be on the order of magnitude of 1, it has to be 1 exactly. Alright, it has to be 1 exactly. Alright, so this term has to be 1 exactly. Alright, so what does this imply? This implies that psi naught actually takes a interesting form here. Psi naught equals to nu L over delta P. Okay, psi naught equals to nu L over delta P. That's a sort of an exact way of putting it. Alright, so okay, here we still have a lot, we don't really know what delta P is, right? Delta P is still something we want to calculate. Let's put it in terms of variables that we know. L is something we can sort of consider independent variable. Nu is something we can consider independent variable. Delta P is not really independent variable per se, because this delta P actually depends on the length of your flat plate. Alright, so how do we get rid of dependent variables? So this is, in this case, delta P is this so-called dependent variable. We kind of want to get rid of it, because of course we don't know how delta P actually evolves yet. Okay, So let's get rid of it. How do we get rid of it? We again use our relation, remember, Reynolds number, mu delta P. Okay. We use our boundary layer Reynolds number, and that's the Reynolds number based on the y velocity, and we assume creeping flow in the upward direction. If you can remember, this is what we did, and we also proved Re delta. This one was quite a few videos back. Okay, we also proved that Re delta is u infinity L over nu, and then what do we multiply by? We multiplied by delta P squared over L squared, and that's equals to 1, or rather math cal O, order of magnitude of 1. Alright, so this is one place we can look to actually determine what we can do. And of course the other place is just well, we can try to get rid of delta P completely by looking at the continuity equation, but that's a bit of a waste of time. Alright, but it's not exactly a waste of time. You can go through it, but you'll find that from continuity equation, and also in the same stroke, if we were to look at the continuity equation here, this 2D continuity equation, we are basically looking at the and if we non-dimensionalize it, we will get the same relation that we got from the original continuity equation. And what was that relation? Let's see. I'm going to go back a little bit. Yeah, we will get this relation here, that this V naught equals to U infinity delta P over L. So there are two unknowns we don't really know. One is the characteristic velocity for the y direction, and one is the characteristic boundary layer length at that point. So that's not going to help us. And just take my word for it, when you non-dimensionalize this, you're gonna get exactly the same result as when you non-dimensionalize this, because the size over here actually cancel out when you non-dimensionalize them. So it's not very helpful. Okay, so that's why I would say it's sort of a waste of time, so to speak. Alright, but so I say from continuity equation, previous also similar to I'll say, yeah, from the continuity equation, what you will get is V characteristic equals to U infinity over L times delta P. Alright, so that's not really going to help. So what instead we can do is to get rid of our delta P right here. Okay, so what's helpful is to use the physics. Okay, we use the physics of the boundary layer, and we say the i.e. Creeping flow in boundary layer. Okay, we use the creeping flow thing in the boundary layer in order to get this done properly. Okay. Alright, so the other assumption we make, is that RE delta equals to 1 exactly. Alright, this is a okay, reasonable assumption, but anyway, it's just to help us with some maths. Yeah, I know it looks a bit arbitrary why I'm doing this, but you will see. Okay, when I substitute all of this into the equation above, it will start to make a little bit more sense. But yeah, let's just try first to get rid of this delta p. Okay, so we make delta p the subject. Okay, RE. Okay, never mind. Let's do RE delta equals to U infinity. Okay, delta p squared. Okay, I'll bring the delta p squared out. U infinity nu and L at the bottom, and that's how you get it. Okay, and if we make delta p the subject, and that will just equal to square root of RE delta. Okay, square root. So I have not done the delta p equals to, Reynolds number equals to 1 assumption yet. I'll just substitute in straight, and you can see what happens. Alright, so this is what the delta p will be like, and I can just chuck that in. Alright, chuck that in, substitute, back, and let's see, psi naught equals to fraction nu L over delta p, and that's equals to, you just substitute this in, and I'll just copy and paste delta p in. I'm not going to do too much here. Alright. There you go. Okay, so what's next? So we can bring this 1 over RE out. It's 1 over the Reynolds number delta out. 1 over square root of Reynolds number. Okay. I just copy and paste everything. Yeah, I did. Alright, yeah, so we are almost there. Then let's do some term cancellation, top and bottom here. So this U naught will, U infinity will go on top, and then the terms here will cancel as well. Oh boy, I think I'm running out of time. I don't want to drag this too long. So I'll stop here. I'll continue more on the next video. So thanks for watching. See you guys again. Bye-bye.